Hi Year 13s, we're looking at polynomials still here, and today in particular looking at conjugate pairs. And there's a few definitions here, but basically the gist of what we're interested in is that when you've got complex conjugates in a polynomial, when you expand them, you always end up with a polynomial that has coefficients that are real. Okay, so there's a couple of examples here. This we have a conjugate pair of roots, and you can see that the polynomial that they form when you expand it is real, whereas the example underneath you've got a pair that aren't a conjugate, and as a result you can see that we've got a non-real coefficient in there with the polynomial. Now this becomes quite useful when we are solving or factorizing quartics. So in this example here, it's asking us to determine the roots of this cubic, given that this is a root. And so let's just consider what we've just learned up here, which is if we have a conjugate pair, then our polynomial has real coefficients. So that works the other way. If we have real coefficients, then if we can often have a conjugate pair of roots. Now I say often because sometimes we'll have real roots, okay? But when we've got one complex root and real coefficients, then there must be a conjugate complex root as well. So with this example here, because all of our coefficients are real and we've got one complex root, that means, so I'll even write that down, so we'll say z1, or no, I should say x1 because we're working with x's here. So our first possible solution is negative 3 plus 2i. So that means that straight away we know that another root is going to be negative 3 minus 2i. And so it's asking us to factorize a polynomial. So in order to factorize it, we're going to need to work out what our third root is. And we're going to take cues from our polynomial, and we'll look at that last part of our polynomial. So if we just think about how it's going to factorize, if these are both roots, then our first two factors are going to be x plus 3 minus 2i. Just notice the difference in the signs there, so I've just sort of jumped a step there. And then x plus 3 plus 2i. So those are the first two roots. And then the third root is going to have to be 2x because our leading term has a coefficient of 2. So it's going to be 2x, and it's going to be minus something. And that something will times with these parts to make 39. So you can form a little bit of an equation here. So let's write this out. So 3 minus 2i times 3 plus 2i times that last root, if you like. So we'll just we'll call it x3, even though that's not actually the root. I'll call it x3 anyway. All of that has to equal 39. Okay, notice I've dropped the negative there because I've dropped the negative here as well. Okay, no big deal, just convenient. Alright, so expanding these first two brackets, we're going to have 9 minus 4i squared, and that's all timesing our third root, equals 39. So I squared is negative 1, so we're going to have 9 plus 4, which is 13, so 13x3 equals 39, and so our third root, if you like, is going to be 39 divided by 13, which is 3. Okay, but in terms of a root, because we've got 2x there, our root is actually going to be 3 over 2, so I'll write that in, that 3 over 2 is our last root. And so now it's asking us to factorize, so that just means we need to write this whole thing out in full. So I'll write that down here. So we're going to have 2x minus 3 times x plus 3 minus 2i times x plus 3 plus 2i. And that's it, and that's all there is to it. So it's quite useful for determining other roots, but also for factorizing, and I'll leave you to have a go at those examples there. As per always, guys, if you've got questions, just flick me an email or ask me in class, and I'm going to build up a bit of a resource over here in the helps scrapbook, so you can shoot over there and have a wee look. Like I've got one example there that I've gone through, and that's a good resource to use. But other than that, get started on exercise 12.09, and I'll leave the video there.